Okay, this is where we ended yesterday. pH, power of the hydrogen ion, that's where we were. Really, before we go anywhere else, on one of your discussion questions, I feel like I need to just address that because don't think we have. We did talk about a calorie, the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. What we didn't talk about was a couple of things. One is called specific heat. That's one of your discussion questions that you have to write answers to. And by the way, that's all fixed now. Our Blackboard person who's head up all of Blackboard, that was acting so weird and she couldn't figure out what in the world was going on. And she messed with it and kept correcting it, and finally it was like, what the? Anyway, she got in touch with the Blackboard people of the world and said, what is going on with this? And so they said, okay, this is what's happening. So anyway, it's totally fixed. So you can create threads, you can click on other people's responses and respond to those. So that's all fixed. So that's cool. Glad we did that. On one of those, it does say listed 2 forms of radioactive decay. I think omit that one. Don't even do it. On one of the discussion forums, it says something about radioactive decay, the 2 forms. Do not do that one. That'll cut back a little bit because I know you're trying to get all those done. We're getting pretty close to test time. I know we're almost finished with Chapter 2. Chapter 3, we'll, get that done. And when we're finished, then of course it's test time. So I don't have a test date yet, but when we get closer to that time, I'll let you know about that. But on one of those discussion forums, I believe it asked you to distinguish between specific heat, a small c calorie, and a capital C calorie. And I know we talked about a small c calorie, and we didn't talk about specific heat or a capital C calorie. Let's talk about capital C calorie first. That's the easiest. A capital C calorie is actually the same thing as 1,000 small c calories. Which is the same thing as a kilo, which means 1,000 calories. So what that means is if I had 1,000 milliliters of water, which is the same thing as 1 liter of water, and if I wanted to raise the temperature of that, increase temperature of that entire liter by 1 degree Celsius, it would take actually 1 capital C calorie to do that, which it would take 1,000 small c calories. If you have 1,000 mils of water, it takes 1,000 calories to do small c calories to increase the temperature by 1 degree Celsius. So anyway, they call that a capital C calorie. Food is actually measured in capital C calories, but when you see it written, say like on the side of a cereal box or whatever, it doesn't say that. It doesn't put a capital C. It just puts it like a small c. That's actually misleading. There's a lot more calories than what they're showing you there. So just so you know that. Specific heat is very similar, but when you're talking about calories, whether it's small c or capital C, that only refers to water. If you're dealing with specific heat, that really refers to anything specific heat. Specific heat is amount of, and that's just abbreviation, amount of heat, triangle is heat, required to raise the temperature of anything of a substance is the way I usually put it. of a substance, and that, of course, is 1 gram of that substance by 1 degree Celsius. Okay, so you may be holding a pen, and so when you picked it up, that pen was room temperature, whatever that would be, about 21 degrees Celsius, probably, somewhere in that neighborhood. I don't really know what the temperature is in the room. I don't normally pay attention. People go, it's really hot outside, and I go, is it? You know, it's really cold out there. I'm like, oh, is it? You know, I don't pay any attention, right? If I know it's going to be cold, I put on a big old, you know, coat, and if it's going to be hot, I dress for that, and you know, I go from a cool or warm building to a cool or warm car to a cool or warm house. You know, I'm not outside playing in the fields, you know, that I used to do when I was younger. You know, I don't spend time outside a whole lot. Although if the weather's really good, I will. I love to spend time outside if the weather's good. I would refer to your notes more than the book. You know, a lot of people on the discussions, they like to give me a book answer, and it's not like I won't accept it, but you won't get full credit. If you give the answer that I give you, you will get full credit. So if I'm giving you a specific explanation, that's the way that I see it. You know, anyone can memorize something out of the book and just put it as a discussion forum answer. I understand that. And then on the test, you know, you will have to also be answering those questions, at least 2 or 3 of those questions. You'll do that down in the synapse from memory. But if you're just memorizing something and giving me that back because you've memorized it, I don't know that you really understand anything. And basically, you could just memorize whatever I give you and hand it back, I suppose. But I feel a little bit more comfortable that you might understand it if you're giving my answer instead of the book's answer. Maybe that's just stupid, but that's how I feel. So I would prefer that you do that. And again, you know, if you want to use the book answer and just memorize it and fire it back at me on the discussion on the test, I'm not saying you won't get points for it, but you're probably not going to get full credit because I just want to know that you understand the concept. That's all I'm after. I don't care how you say it. The term, you know, as far as, you know, the way you explain it, as long as you explain it to where I know you understand it, that's all I'm after. People are always like, well, it's science, and I have to sound very scientific, and, you know, so I want to make sure I sound, you know, brilliant and all that. I'm just like, no, that's not what it's about. It's about explaining a concept. That's all it's about. And if you do understand it, then there's a gazillion ways you can explain it. You know, it's like I don't worry about, okay, I've got to describe specific heat. Am I going to do that? I don't worry about it. I understand the concept, so not a problem. I can explain it several different ways. I don't ever probably explain it the same way, but so that's really what I'm after on those answers. Okay, so again, going back to that pen, you know, if you're holding a plastic pen, when you got it out of your backpack, whatever, it was about 21 degrees Celsius. Once you held it, your body temperature is so warm, 37 degrees Celsius, your body temperature. So it was 21 degrees Celsius, and you're holding it at 37 degrees Celsius, your body temperature. So you know the temperature of that plastic is going to go up. Okay, so for every gram that you have of plastic that you increase by 1 degrees Celsius, then that is, you know, the amount of heat that it requires to increase that amount of plastic, 1 gram of that plastic by 1 degree Celsius. The amount of heat required to do that is, you know, and it may, who knows, I don't know what it would take. I don't know the specific heat of plastic. and I'm sure it depends on the plastic. Lots of different densities of plastic out there. But then, so that's a specific heat of that particular substance. You know, what's the specific heat of gasoline? Not water. You know, you throw a match in gasoline, how long does it take it to go from room temperature to really hot? Very, very fast. You know, I'm one of these people that if I want to get a fire started in my fire pit, I have a fire pit, I have a couple of fire pits, you know, I throw a bunch of logs in there, and then people think I'm crazy because I'll get gasoline, and I just like soak it down with gasoline, and I say, okay, get back, you know, and I light this, you know, and put everything away, light this match, and just pitch it in there, and it goes, you know, man, it's lit. You don't have to worry about it going out. You know, it's done completely. I don't try this at home. They'll tell you, and they always look at you like you're a nut. You're using gasoline to start a fire? Oh yeah, it'll work. I don't have to worry about it starting. It will start. Yeah, no questions here. So, but probably best not to explain that to people. But anyway, so specific heat of gasoline is very, very low. Alcohol or compounds with a lot of OH groups, like an alcohol or a gasoline, they tend to have very low specific heats, and temperature rises very, very quickly, like isopropyl alcohol or vodka, or you know, any kind of alcohol, beer, so forth. Temperature changes very, very quickly. You know, you don't have to leave beer out very long before its temperature changes really, really quickly. If you want to chill a bottle of wine, it only takes 7 minutes in the icebox. That's it. 7 minutes. You got it. Beer, about 7 minutes. That's all. You know, take it, put it in there. 7 minutes. You've got a cold beer. That kind of thing. Okay, so that's specific heat. It can be anything, just not. And there is specific heat of water. That is called a calorie. That's really a small c calorie, specific heat. So it can be, you know, metal. You know, how much heat is required to raise the temperature of 1 gram of a metal, depends on the metal, by 1 degree Celsius. That would be the specific heat. But if you're talking about water, to raise the temperature of 1 gram of water by 1 degree Celsius, that is 1 calorie. All right. So calories is a heat measure, and the standard for that, of course, is they use water to do that. All right. So those were some things that we didn't get into that we probably needed to talk about. Okay, we did talk about acids and bases. We had already talked about salts. That's one of the other discussion forums that you have. So hopefully you'll be able to do that one. And like I say, you can work off each other. This person answers something that you think, well, you like the way that they put that. It's kind of better than the way you put it. You know, it's like you can pull from each other and come up with a really, really nice answer on those. And I think that's great. You know, and again, as long as you're answering the concept completely, I'm fine with it. It doesn't have to be 3 pages long or anything like that. I'm not looking for a length. I'm not counting words. I'm not doing any of that. I'm just reading through it going, do I feel like they understand the concept, you know, of capital C calorie, small c calorie, specific heat. And if they understand it, if you understand it, then full credit. There we go. And that will probably be worth 60 points. The multiple choice, which you'll do in here, maybe. We probably won't now that I see how exactly short 8 weeks actually is. It's amazing. You'll probably do that down in the Synapse as well. So it's just really crazy. I'm starting to panic a little bit, but not completely, not just yet. This is not the time to panic for me. Y'all don't have to panic ever. I'm the one that has to worry about getting you through this in 8 weeks. You know. Although y'all do have a lot of work. I mean, it is really, so much of it went on your backs. And, I'm like, man, these students, it's different now. It's a different ball game for you guys. And it's going to be interesting as to how it all plays out. The lab tests, most people did really well, and I was just really happy about that. I was like, man, they're doing it, and you had to do it. I couldn't do it for you. You had to watch the pre-labs, and you had to know what's going to happen before you walk into the lab, because I don't have time to do. You only have an hour and a half. Used to, we had 3. Which was great. I had plenty of time to explain stuff and go over and do examples, and we don't have it. We don't have it. I would normally have a total of, I guess it would be 3 hours a week, but that's over 16 weeks for lecture. Add that up. Now I have actually 4 hours per week for 8 weeks. You don't get near the time in class, so you've got all that you have to do. I'm changing it a little bit for the next exam. I'm giving you the full PowerPoint, but that's not what I'm going to cover in lecture. I'm stripping the PowerPoint down to what I think is most important, but you're going to need to read the complete full PowerPoint because you're responsible for that. Obviously, you need to read the book because you have reading questions on mastering. So, again, it just, in order to get through it, it throws more on the back of the student. In one way, everybody that I talk to about this outside of the school environment, they go, I like that because that makes the student responsible, it makes them accountable, and the people that I talk to with regard to this, and they may not be in education at all, just, whatever, just general people that I talk with, they go, they like it. They think it's a pretty good idea because it does make a student responsible and accountable. And I think that's something that we sort of got away from in education, and it really was thrown all on the back of the student. And I don't think that was really good to do it that way. So we'll see. I hope it works. I really do, because I think a student will get more out of it. I think he will learn a lot more, and I'm all about that. Seriously. I mean, you may think that's a little, I don't know. You may think it's kind of hokey, but I am. I want you to get a good education. I think that is important. I wouldn't trade for my education. A friend one time who was a woman that I highly respected, brilliant woman, who was actually vice president of this college one time for a long time. Anyway, she asked me, and you may know this story, but she asked me, what do you consider to be the most valuable investment? And I said, land. She said, well, that's not a bad one, but I think education is. Because the government could come along and take your land anytime they want it. They can take your house, they can take your car, they can take everything you own. A government can come in and do that if they really want to. The only thing they can't take away from you is your education. They can't get that out of your head. No one can ever take that from you. They can't get it. Once it's in there, they can't get it. And as long as we have an educated population, we're not going to let them take over. We are not going to let the government take over the population. We will not allow them to do it. So education is critical to the survival of the common man. It is super critical. And the older you get, the more important that actually becomes to a person. It's like, no, we got to keep an educated population. It's very important. So, again, for people your age, maybe that's very hokey, and it very well may be, but it is what it is. And it's not hokey at all, really. When you get a little bit older, you'll go, yep, my kids better get a good education. I'll kick their ass. That's the way that is. Okay, anyway, I'll get off my soapbox. But let's talk about a buffer. buffer keeps a pH constant. Okay, for example, we have to maintain a constant pH in the blood. Have to. We don't have a choice. You have what's called the limit of life. Limit of life. I'm going to go with a different color. I'm kind of bored with that one. Here we go. Let's see what this does. Limit of life. Okay. So, and this is blood, BLD, common abbreviation, BLD for blood. Nurses use it all the time. Doctors use it all the time. Might as well get used to it. So many of you are going into a health field, or you want to get into a health field. Just get used to some of these things. Blood pH. Blood pH has a very narrow range. It ranges from a 7.0 to a 7.8. That's it. 7.0 to 7.8. That's a very narrow range. It typically stays right at 7.4. Very close, if not exactly on 7.4 pH. Okay. If your pH drops below 7.0, that's called acidosis. That can kill you very quickly. Acidosis. If it goes above a pH 7.8, that's called alkalosis, and that can kill you very quickly. You can die if your pH of your blood drops below 7. You can die very quickly if the pH of your blood goes above 7.8. So what if you have pizza and a beer? America's food, right? I love it. I love it. Absolutely. You know, pizza and a beer. Very nice. Those are simpatico. You know, that's just like very good. I have to watch my language. Now that I'm recording, used to I'd just come out with things. I can't do that anymore. They've stifled me. They've recorded me. Okay. Oh well. Oh well. I will adjust. I will adjust. So pizza and a beer. Beer has a pH of like 5. Pizza sauce, tomato base, it's very acidic. Okay, so when you eat that, you drink that, you're getting a lot of acid. Well, that absorbs into your blood. So, you know, if you didn't have something to keep the pH of your blood within this 7.0 to 7.8 range, that's your limit of life. Keep it pretty close to that 7.4, you'd die. You know, if you're eating acidic material, like pizza and beer, you know, if you didn't have buffers, your pH would drop. You'd be dead. You know, a couple of slices of pizza and a beer, you'd die. Wasn't that good? No, it's good. I don't know if it's worth dying for, but maybe so. So buffers keep pHs constant. What they do if the pH drops, that means it's releasing more hydrogen ions. That's what acids do. They release hydrogen ions. Buffers attract the hydrogen ions. So that's what they can do, attract the hydrogen ions. And the acids release hydrogen ions. So if the buffers attract the hydrogen ions, then, of course, the pH is not going to drop. So that's one thing buffers do to keep the pH, in this case, at 7.4. Well, what if you eat basic compounds? Like, for example, what if you chew some Tums? You have acid indigestion, something like that. Maalox or all kinds of things you can get. Those are base compounds. Well, okay. Then that's going to absorb across, go into the blood. I mean, that's everything we eat and drink is going to move across the intestinal tract and go into the blood. Well, okay, you eat Tums, that will absorb, go into your blood. Of course, it does neutralize the acid of the stomach. But still, if you had enough, you could actually absorb the base into your blood. So the pH would start to go up. So you would actually be absorbing too many, say, hydroxyls, OH, with a minus on it. Like sodium hydroxide is a base, potassium hydroxide. The OH is a common base unit. The OH in parentheses with a negative. That's a base unit. Buffers can attract that also. So if the pH starts to go up, the buffer grabs the OH negatives and grabs a hold of it. So that doesn't, so the pH is not going to go up. It keeps it constant. It's a very good thing. We have all kinds of blood buffers. You have buffers in cells. You have buffers outside of cells. You have buffers in your blood. Buffers are very, very common to anything that's alive. They have to have them, or the pH would change so quickly that it would destroy them. The pH of the oceans are changing very, very quickly, and it's having some drastic effects. The coral reefs are dying off. You'll see that. Fishes are dying. Fish are dying. There was someone on, I was watching David Letterman last night, and it was Bill Maher, who's a little out there, I understand. But he came out with a statement that by the year 2050, which is not too far away, you'll be here, all the fish in the ocean will be dead. Whoa, in your lifetime, I'll be gone. But, you know, in your lifetime, all the fish in the ocean will be dead? Are you kidding me? No more mahi-mahi, you know? No more, shark steaks? Man, this is going to suck. Not going to be good. I don't know if he's right about that. I don't know how you can make those predictions. You know, I try to actually pull up predictions, and I've tried very hard, but it's very hard to get them. I tried to do predictions yesterday. Yes, sir. Well, acidosis. Yeah, you don't have to know that, but you might as well put it in. Acidosis and alkalosis, if it goes above 7.8, it's certainly not going to be on the test, but it's good information. Stick in your head. Once you know the limit of life for blood, pH. Okay, this shows you some things that are acids and bases, and of course neutral, pH 7, there is going to be, of course, water. You have an equal number of the acid unit, which of course would be the hydrogen ion unit, and then an equal number of the base unit, which typically is the OH negative unit, so equal numbers. And then, of course, if you go from pH 7 to pH 6, you have 10 times more hydrogens. So that's just human urine, saliva. It's, you know, it's a little bit acidic, not much. Rainwater, look at where that is right now. pH of 5. Tomato juice, 4. Tomatoes are pretty acidic, like I said. Pizza. Then you get into cola. Cola, 3. Oh my goodness, that's pretty acidic. I drink 1 a day. That's all I will allow myself. Lemon juice, gastric juice. Your stomach fluid is somewhere between 1 and 2. And then you get into battery acid. Whoa, pretty darn acidic. Okay, I can remember working on a battery, you know, like high school, driving some old car that was handed down from my brother, which it was handed down originally from my parents to my brother, and then I ended up getting it. So it had problems. You know, battery all corroded up. You know, I'd have to go out there and mess with that battery. And the first time I ever did that, I remember doing that, and then just, I was what? 17, 16 years old. I just wiped my hands off on my jeans, and then at night throw them over in the corner somewhere. The next morning pull them on, and they're just got like holes all through them. You know, of course, y'all would probably think that was very cool. In our day, of course, that was not cool. But we couldn't have holes in our jeans. That was not a cool thing. But I have no idea what's cool these days. They don't really even care. Doesn't matter at this point. I'm almost dead, so that's okay. Like I say, any moment I could go. I could have a heart attack right now in the next few minutes. Class is dismissed. Just walk out. It's done. It's done. And it's good. It's good. Not a bad thing. All right. So oven cleaner. Oh my gosh. You ever clean oven. That's some pretty basic material. You get into oven cleaning. I don't like to do it. That's why very rarely do I do that. All right. So here's a problem. Obviously, with the production of all the carbon dioxide, we're burning the fossil fuels with our automobiles, and by doing that, we're releasing a tremendous amount of carbon dioxide. And that is, carbon dioxide actually forms a layer around the Earth. So let's say this is Earth. Put a big E on it. So Earth. And let's say this is the layer of carbon dioxide. Well, the layer used to be like this. Okay. But what we're doing is we're making the layer much thicker. The problem with that is carbon dioxide acts like a blanket. So sunlight can get in. Here's Mr. Sun up here. Sunlight can get in. That's a very short wavelength. But heat is a long wavelength. It's a very long wavelength. And the heat cannot get out. This is heat. This is light. Light can get in, but the heat cannot get out. Some of it does escape. That's true. Some heat. I'm not saying none of it will escape. Some heat does go out into space. But some of it is trapped. And the thicker the layer of CO2 that we have, the less we're actually going to let out. Light can still get in, but the less heat will be able to get out. Of course, what ends up happening is we end up with global warming, which is why we've been in a drought for 10, 12 years. This is why California is in like a severe drought. They're in what is called a severe drought. If I were living in LA, I would get out. These people, like you see these movies, I don't know if you watch them, $1 million listings and things like that. People buying like, $12,000, $40,000 homes in Los Angeles. I'd be like, no, I wouldn't spend it there. No, if you've got that much money, I would certainly not buy it in Malibu, which is beautiful. The beach is great. I've been there, swam at Malibu Beach before. My nephew and I were so far out. We were out there where the surfers were, and the lifeguard had to swim out there, and he was like, "Hey guys, y'all can't be out here. This is for surfing only. Y'all have to be." And I'm like, "I'm so sorry. I didn't realize we swam this far out." Had to be. The lifeguard had to get on to me. And I felt so stupid. It's like, I'm so sorry. I didn't mean to do that. But yeah, all kinds of things going on, and that's horrible. And, not so horrible for me, but for you guys and for your children, it's horrible. About 25% of carbon dioxide is absorbed by the oceans, and that's called ocean acidification, because this is really what happens. The CO2 combines with hydrogen, and you form a bicarbonate, which is negative, and you tend to drop off that hydrogen is what's going to happen. Therefore, you acidify the oceans, and this is what you're really seeing here, lowering the pH of the water, which is why the predictions are, and of course this is a coral reef right here, which should have all kinds of color and all kinds of fish swimming around it. You can take, and they have taken plenty of them, satellite photos from, of course, space of Earth, and you can see all the coral reefs are just dying off, and that's a habitat for all kinds of, all those beautiful fish that you have with all the spots and the stripes and different colors, and that's what they all are. They're coral reef fishes. And if you go to a coral reef, which I have several years back, thank goodness I did that several years ago, in a couple of different places. One I remember was Hawaii, and and you can snorkel and see the coral reef fish, and they'll come right up to you and kind of bite at your finger, and all kinds of colors, and amazing, absolutely amazing. Anyway, you better rush out and do that real fast. I would get on that, like maybe this summer, and maybe take an underwater camera. My cell phone will go down to 6 feet, which would be plenty, as long as you can get it under the water, you can take video. That would be cool to do. And save that for your grandchildren, because they probably won't be able to see that, which is horrible. Horrible, bad, horrible, sickening, don't like it. But until we all stop driving these gas-sucking automobiles, that's what's happening. We should all be driving our electric power. I can't wait till hydrogen power comes out. I think we're going to have to have all kinds of really horrible things happen before they go, you know what? We need to really get serious about this hydrogen power. And then all of a sudden it's like, everything's hydrogen powered. I keep telling you, that's where you need to invest, right there. Hydrogen power. I promise you. You're going to be one wealthy person. But, college students don't typically have a couple of grand hanging around. But, you can scrape it together. I mean, Okay, so now we're on chapter 3. Finally, we get to chapter 3. Today is the last day we should be actually finished on my schedule with chapter 3, and we're just now starting it. Chapter 3 is pretty long. I have stripped it. And again, on the other PowerPoints, I have left the entire PowerPoint, loaded the entire PowerPoint onto your modules, and I'm stripping them down to what I think maybe I can do with class time that we have. And what's killing me is I like to have so much fun in class, and I'm not being able to do that. I keep trying to have fun, and then I keep thinking you don't need to be doing that. You really shouldn't be doing that. You're taking time away from these people who need your time. You're doing them a disservice, which it is, basically. It is. Okay, so we're really getting into organic compounds, things that are carbon-based. Anything that is live is built around the element carbon. So you have carbon bonded to carbon, bonded to carbon, bonded to carbon, and you also have these things called hydrocarbons. You have carbon bonded to hydrogen that bonds to another carbon that has some hydrogen on it, that bonds to another carbon that has some hydrogen on it, and that's kind of the building block for anything that's alive. It's called organic compound, and they have a whole field of study called organic chemistry that most of you will take. And I loved organic chemistry. I wasn't particularly fond of the inorganic, but organic chemistry I liked because it was very applicable to the living world, and I thought it was cool. Anyway, so those are carbon-based compounds is what we'll be working with. And so carbon has a total of 6 protons if you look at it on a periodic chart, but anyway, I'll just do this. Carbon has 6 protons, 6 neutrons, 6 electrons, 2 in the first shell, 1, 2, and then 4 in the second shell. 1, 2, 3, 4. Well, if I want to have a filled outer shell, I need 4 more electrons. Okay, so it typically covalently bonds with 4 other atoms. So I could share 1 electron from atom X, we don't care what it is, doesn't really matter, and I could share another electron from another atom, call it atom Y, whatever that is, and I could share another electron from atom Z, and I could share another electron from another atom X, whatever. So that would fill up. You'd have 2, 4, 6, 8 in the second shell. So it tends to form 4 covalent bonds. So you would have carbon that bonds this way, this way, this way, this way. And so you're bonding it to something, to something, to something, to something. So it does tend to form the 4 bonds because of it does have 6 electrons, 2 in the first shell and 4 in the second shell. So you need 4 more electrons to fill up that second shell. Bless you, bless you. That's a bless you again. I sneeze in 3s too. I'm a triple sneezer. Some people are. All right. So you can branch in 4 directions. It makes a wonderful thing to build around. Now, the carbon is not the most common element on the planet. It isn't. So it's kind of, you think, well, so why did life evolve around carbon? Well, because you can bond to the above it and below it and to the side of it and the other side of it, you can form 3-dimensional structures. But there are other things that you can do that with. And the most common element we have on planet Earth is silicon. Makes up dirt. Silicon dioxide. Dirt. Very common. I don't know if you've noticed it, but it's out there. Just go outside. Yeah, very common stuff. But it's very heavy, which means had we evolved with silicon, we'd be like these rock things that kind of walk around. Maybe when the spaceship lands from outer space, they'll be like rock creatures. That's kind of what I see. I'm like, spaceship lands, because it'd be so heavy. These rock things come climbing out of it. I don't know. Oh, the rock people look at each other and go, oh, that's a really hot rock person. Look at that. Look at her, man. What a babe. Look at her rock breasts. I'd love to get my rock mouth around that. No, I'm just messing. Just messing. Okay, just messing. It's what I like to do. I just don't get a chance. I don't get an opportunity. They won't let me. I don't have enough time to be crazy. Oh man, it's so hard. Oh yeah, it would be, wouldn't it? Okay. Rock sex. Can you imagine? Oh my God. Yeah. Oh yeah. Oh, that was great. Oh man. I think I left some pebbles. Oh man. Whoa. Oh, that mind does go out there, doesn't it? As long as you're over 18 and you're not complaining, we're all cool. It's all good. If you complain, I'm in trouble. All right, but here again, you're looking at the 3-dimensional structure of carbon. Now, it is bonded with hydrogen, but it has kind of what they call a tetrahedron. It's in 4 directions. It's kind of hard to draw that, but anyway, 4 directions. These are going back. This is coming out. This one's going up. But it's a great building block for sure. And like I said, it is a lightweight element. So you end up getting hydrogens bonded to carbon, and they're called hydrocarbons. And so many of the molecules that we'll be working with are going to be hydrocarbons, hydrogen bonded to carbon. Totally makes sense. Okay, so it is the skeleton. And there are different ways that you can bond carbon. You can bond carbon to carbon to carbon to carbon. You can bond it in a straight chain. We'll show you a diagram of that. You can branch it. You can form rings with it, and we'll show you that. So that's actually, I think, the next slide. It isn't the next slide, but we'll get there. Let's talk about this thing right here, an isomer. Isomers are elements with the same chemical formula, like, for example, C6H12O6. Okay, but this could be either, say, glucose, which is a sugar, anything that ends in an OSC that tells you it's a sugar, or it could be fructose, but you've heard of high fructose corn syrup, and a lot of people are, they're like, don't drink that stuff. It has fructose. They've actually proven there's no difference between a sugar and a sugar and a sugar. Doesn't really matter. So don't worry about those. But they have the same chemical formulas: 6 carbons, 12 hydrogens, 6 oxygens, but they're put together differently. They look completely different. They're called isomers. Same formula, different structural arrangement. They're put together in a different way. It's like working with Tinker Toys. You can build it this way or you can build it with that way. Given the same number of little wooden structures that attach to the wooden sticks, you can put them together many different ways. All would be isomers if you have the same number of wooden structures and wooden sticks. They go together in different ways. All right. It's more fun when I get to kid around. Okay, now, if this animation will work, which it isn't, gosh, I don't know why. Man, it works in the office. It does not work in here. Let's see if this will work. File, no. Okay. Not going to do it. Man, I wanted you to see that. It's very cool. Just believe me, it was very cool. Okay, so here are some isomers. These are structural isomers. If you count the carbons, 1, 2, 3, 4, count the carbon 1, 2, 3, 4. If you count whatever else, you have the same number of carbons and same number of hydrogens and same number of, say, oxygens, and it's just put together differently. Same thing here. These are geometric isomers. Okay, this is probably oxygen here. And here they're at, of course, a diagonal, and these two are going to be on the same side, geometric. In enantiomers, this would be like right hand, left hand. Those are enantiomers. So I can build a molecule that would be, say, like, basically built like a left hand and one that looked like a right hand. They're exact copies, except one is a mirror image of the other one. Can do some really horrible things. They used to make a birth control pill, and they didn't realize, though, that it had an enantiomer, and it was so like a mirror image of the other one. One of them worked just wonderfully and didn't cause any problems. The other one, once the female stopped taking the birth control pill and became pregnant, she gave birth to a deformed child who was just like, the legs were incredibly short and the arms were incredibly short, and the body, and it just had all kinds of mental problems, and this was back in the 50s, which when I was born. So thank goodness my mom was probably taking the right, maybe she wasn't on any, she was probably on some sort of birth control, because there are only my brother and myself. Should have had 50 children otherwise. You would think not on any kind of birth control. I would hope my parents were active. What was that? That was Tinkerbell. Tinkerbell, take me with you. I love that. Peter Pan. Man, talk about a cool, that was cool. I love Peter Pan. Anyway, okay, so here's some carbon to carbon. These are straight chain forms. You have carbon to carbon. Now remember, carbon is going to have 4 bonds because it only has the 4 electrons in the last shell, last orbital, last energy shell. So this carbon is bonded to this hydrogen, sharing an electron with this hydrogen and this hydrogen and this hydrogen, but it also is sharing its 1 electron with an electron from that hydrogen, from that carbon. So this carbon is also sharing 1 electron with this carbon, and with this hydrogen, and this hydrogen. So that would be a stable compound right there called ethane. Here's propane. Propane is C3H, let's see, 6,8. So this is C3. If you wanted the chemical formula, C3H8, put together like this, you're working with propane. Butane would be C4H10. That's a 4H10. Four carbons and then 10 hydrogens all attached to those carbons. That's butane. Put a butane lighter if you're trying to light something. Okay. If you put a double bond in it, now remember, carbon always has to have 4 bonds. So there are 2, 3, 4. There are 2, 3, 4. Has to have 4 bonds. This one is 2, 3, 4. This one is 1, 2, 3, 4. Hydrogen only has 1 bond. It only has 1 electron, so it's only going to have 1 bond. Here's an isobutane. It's an isomer. Same number of atoms, 4 carbons, butane, and you have 10 hydrogens. Same thing here. 1, 2, 3, 4 carbons, and if you count hydrogens, it will be 10. Number of building blocks just put together different ways. It's an isobutane. Anyway, so different ways to put those things together. And all right, here is 2 different steroid compounds, and this is very interesting. One is a testosterone, which is the male hormone. Now, females produce it too. Females, though, only produce this at the adrenal glands, adrenal. And you don't have to know that, but the adrenal glands are found basically on top of the kidney, kind of on top and towards the midline. Little, fairly small glands called adrenal glands. And so females do make a little bit of testosterone, but it's not a whole bunch. So. And testosterone has masculinizing effects. That's what it does. Lower voice, hair production, greater hair production. So, you end up with, at my age, crazy thing. We'll get back to this tomorrow where the battery died. But it has masculinizing effects.